MPC machine learning library. Now, this one is a little bit interesting for some other reasons, and this is the first thing that I'm going to actually show some data on today. This is going to be the first time I'm showing any data around this. These numbers are subject to change, but the performance of this was just too hot to handle, and I have to show it to others. Essentially, we are relying on an entirely different form of machine learning. Like the way that we're conducting machine learning to fulfill functions like your traditional softmax and everything is done in a way that is actually functional on CPUs. And there's a lot of research behind it, and I'm not going to dive into the full details of that because, frankly, I'm not ready to give away the secret sauce to what we're doing yet. But as all of our components on Q, it will be, of course, open source, AGPL licensed, so sorry any other competitors that want to leverage this for your own tech. If you do try to use it, you will be bound to the AGPL license and you will have to contribute back, and that's kind of our mantra of our infectious license. But let's go ahead and hop over to it. Oh, I have Excel draw up, of course. So what is in this graph is kind of one of the most powerful graphs I've ever seen in terms of the things that we've been building. In terms of raw performance, what you're essentially looking at is a standard data set that's been trained using a model that works on traditional TensorFlow implementations. And so in this graph, you're seeing at the bottom is the amount of time in seconds that it's taking to train. It's a relatively small model, only 670K parameters, but it takes on a CPU implementation of TensorFlow a very long time. Like we're talking about 50,000 seconds just to train this very small model. And on a V100, it takes, a little bit less time. This is a logarithmic graph, so it's still, we're still talking about hours. And then finally on something like the A100, you end up with a still faster time. But our implementation and what makes this so crazy and so like I have to shout it from the rooftops before we actually publish it is that it's actively competitive against an A100 using traditional CPUs. And the reason is that we're not doing the same types of matrix multiplication techniques that A100s do, or V100s, or any other implementations of traditional models. The way that we're performing this mathematics is through another thing, and I'm not saying what that other thing is yet. If you've been a reader of AI papers for a while, you may actually know what I'm talking about, but there is an interesting different technique to implement these same exact functions in a way that works on CPUs, is incredibly efficient, and what is most important for Quilibrium is the fact that it can also be encrypted. And so in other words, these operations can be working on encrypted data without revealing the private inputs of that data, and it works well in an MPC scheme, and it still retains the performance. And that is the absolute killer element to it. And so that's the one thing that I wanted to bring up because that's something that a lot of people have been asking about, which is how are we going to be, oh yeah, sure, we can zoom in. How are we going to be operating in a machine learning world when machine learning is very slow for multi-party computation, which is why a lot of multi-party computation-oriented projects end up just shoving it in a TEE. This is how. And so I can't wait to actually publish the full paper on what is being called Claru, but it is insanely fast.